Hello world, in today's video we're going to continue talking about the universal gravitational law, but in today's video we are focusing more on the application. So we are having a problem over here. Please feel free to pause and try this problem out for yourself. So these are the questions and the last one is somewhere down here. So it says, consider the diagram below showing the sun, the earth and the moon. The earth has a radius of 6,38 times 10 to the power of 6 meters. Then there's the diagram over there. The first question says, state Newton's universal law of gravitation. Okay, I'm not going to state that law, but what I can say is you scored yourself 2 free marks. 5.2 says, calculate the magnitude. So we are only looking for magnitude of the gravitational force of the sun. The gravitational force the sun exerts on the moon. So I'm just going to highlight that. Gravitational force the sun exerts on the moon. Okay. So there's only one equation to calculate the gravitational force, that is Fg equals to G m1 m2 over r squared. So m1 is the mass of object 1. What are our objects of interest? If we go back to the statement, the objects of interest are the sun and the moon. So I'm going to take object 1 to be the sun, and object 2 will be the moon. So ms is mass of the sun, mass of the moon. Remember what r is, and I'm going to keep writing the interpretation of r. R will be the distance from center of moon to center of the sun. Let us see if we have that distance r from the diagram. If we look at the diagram, this diagram is clearly providing us with center to center distances. So that distance there will be 2 times 10 to the power of 11 meters. So that part, which is mostly the most crucial part, is sorted out. Then we can sub in. Remember, G is your gravitational constant. It's a constant. You get it from the data sheet. Mass of the sun, it's given as 1,99 times 10 to the power of 30. You have mass of the moon up here, 7,35 times 10 to the power of 22. And we are given our R. We are being told it's 2 times 10 to the power of 11. Don't forget to square. Therefore, the gravitational force will be... Okay, let me just quickly grab my calculator. Okay, just a moment. 6,67 times 10 to the power minus 11 times 1,99 to the power of 30. Please feel free to punch the calculator together with me so that you can confirm these calculations. Okay, so my calculator tells me that the gravitational force will be 2,439 times 10 to the power of 20. Remember, force is in units of Newton. And they were specific about this gravitational force. We're being told that this is the force that the sun exerts on moon. And we can come to this diagram and even try to draw out this force. So we're being told that this is the force that the sun exerts on the moon. This means that this force is acting on the moon. So if we were to show this force, we are going to show it on the free body diagram of the moon. Question is, how do we get the direction of this force? If you want to get the direction of the force is along the line that passes through these two objects. If it's an attractive force, what I like to do is, unfortunately, I can't I can't do this with my hands. So normally what I like to do is, if I want to get the direction of the force, I am going to put these objects in my hands. So the sun will be on the palm of my left. The moon, I'm going to put it in the palm of my right hand, and I'm going to close up my hand as if I am folding the fist. So what we are saying is the force is along the line between these objects. So what you're going to do is, if the force is attractive, then your thumbs will point towards each other. So let me try to draw out a hand. So these are my knuckles, folded hands. Inside my hand, I have the sun. This is my right hand. These are my knuckles all folded up. Inside my hand, I have the moon. So what I'm saying is, if the force is attractive, I'm just going to ke tlo ntsha di-thumbs. Ke tlo di otlolla, ke tiile ke sekgowa. So I'm going to take out my thumbs in such a way that the thumbs are going to point at each other if the force is attractive. If the force is repulsive, then my thumbs, they're going to point in opposite direction. So what do the thumbs represent? The thumb represents the direction of the force. This is the direction of the force. Which force is this one? This is the direction of the force on the moon exerted by the sun. The direction of the thumb is the direction of the force. This is the direction of force exerted by moon on the sun. And we have said that when we talk about the gravitational force in its nature, it is attractive. That is why my thumbs are pointing towards each other. Okay, so now I'm going to draw out this force on the diagram. So it means that the direction of this force on the moon, the direction of the force of sun on moon. Okay, I'm gonna write it up here. Force of sun on moon. That force is towards the left. And on the sun, the force of moon on sun, that force will be towards the right. Okay, I'm most probably gonna need these force diagrams in a short while. Then the other question says, how does the gravitational force that the sun exerts on the earth compare to that the earth exerts on the sun? So over here we are talking about a gravitational force that the sun exerts on the earth. What are the objects of interest? Object 1 is the sun. Object number 2 is the earth. I can call this object A, this one object B. So we are comparing the force that sun exerts on earth to the force that earth exerts on the sun. In other words, we are comparing the force that object A exerts on B to the force that B exerts on A. And remember, from Newton's third law, we have said that if object A exerts a force on object B will simultaneously exert an oppositely directed force of equal magnitude. So the force that we are talking about here, these forces, they are equal because they have same magnitude. This is according to Newton's third law, and that is exactly what I was applying here. So what this means is, if I take this argument back to the force that the sun exerts on the moon and the force that moon exerts on the sun, these two forces, they have the same magnitude. I have their directions, which we can clearly see from the diagram that they are in opposite direction. So what this tells me is these two forces have a magnitude of 2,44 times 10 to the power of 20 newtons. Okay, let us look at the other one. The last question says, calculate the magnitude of the, I'm interested in this, net force experienced by the moon. Remember what net force is. When we talk about net force, we are talking about sum of forces. And when we talk about sum from mathematics, this has to do with addition. So we're talking about adding forces together here. And this takes us back to the lesson on vectors. Remember, we said if we have, let us say, this vector A and vector B, and we want to add them together, because they are collinear, we just simply add them together and take into account the directions. That is case number 1. If we have case number 2, whereby A and B, they are perpendicular to each other, what we have learned is to find the resultant. Here we are required to apply the theorem of Pythagoras. Okay, so what we need to do is we need to go back to our diagram and check the scenario that we are having up here. So if we go there, we are looking for the net force experienced by the moon. The victim here is the moon. Our focus is the moon. So we are going to draw forces which are acting on the moon. So the first force which is acting on the moon, this is the force that the sun exerts on the moon. But hold on, there's another object there. There's the Earth. Because these two objects, they are having mass. We know from the gravitational law that they are going to exert a gravitational force on each other. So we are going to have another force exerted by the Earth on the moon. What is the direction of the force? Remember, now I have to put these objects in my hands. These are my knuckles. Okay. What I know so far is the gravitational force is attractive. So my thumbs are going to need to point each other. So this is my hand. This is my thumb. Inside this hand, I have the moon. Inside that hand, I have the Earth. So this gives me the direction of the force on the moon. This gives me direction of the force on the Earth. Okay, so if I draw it out on the diagram, I have the force exerted by Earth on moon. Remember that we said these forces, they act along the line between the objects. So this force of sun on the moon is along this line. Force of Earth on moon is along the vertical line. And what we see from the diagram is that these lines, they are perpendicular to each other. So it means we need to apply theorem of Pythagoras to find the resultant force. But before we apply theorem of Pythagoras, question is, do we have the force that the sun exerts on the moon? The answer is yes. We got it from 5.2. Now, do we have the force that the Earth exerts on moon? The answer is no. But can we calculate that? The answer is yes, we can calculate it. Okay, so I'm going to keep this one up here. We said this was 2,439 times 10 to the power of 20 newtons. I just want to erase this part down here. I'm just going to leave out this formula. Okay, so now the objects of interest have changed. We are no longer talking about the sun and the moon. We are talking about Earth and the moon. And when we come here, the distance will be the distance from the center of the moon to the center of the the center of the Earth. Do we have that distance? Let us check from the diagram. The distance was given there. Let me try to erase this so that I can clearly see it. It was given as 4 times 10 to the power of 8. This is 4 times 10 to the power of 8. And we can clearly see from the diagram that this is the center to center distance. So if you want our gravitational force, the magnitude will be 6,6 times 10 to the power minus 11. The mass of Earth, where we given the mass of Earth, yes, they were kind enough. But remember, if they don't give it on the diagram, we should know very well that the mass of Earth should be obtained from the data sheet. Times 10 to the power of 22 divided by r, that is 4 times 10 to the power of 8, all squared. Therefore, the gravitational force will be, calculator, okay, 6,67 to the power negative 11 times 5,98 to the power of 24 times 7,35 to the power of 22 divided by, okay, my calculator says the answer will be 1,832 times 10 to the power of 20 newtons. So if I redraw these forces again, we said this is the force that the sun exerts on moon. I'm going to draw them using tail to head. And we said this one will be the force that the earth exerts on moon. Remember, if I want to add them together, the resultant will be from the tail of the first vector drawn to the head of the last vector drawn. This will be the resultant force, which is F net, or you can call it F resultant or F res. Okay, so what we know is that these two are perpendicular to each other. So if we want the resultant F net, according to theorem of Pythagoras, will be the square root of 1,832 times 10 to the power of 20 all squared, plus the other one was 2,439 times 10 to the power of 20 all squared. If I punch that on my calculator, it tells me that my net force will be, let us see, 1,832 to the power of 20 all squared plus 2,439 to the power of 20 all squared. My calculator tells me it will be 3,05 times 10 to the power of 20 newtons. And voila, there's your answer. So if you looked at the diagram that we had, the bodies we were working with, they were arranged on the vertices of a right angled triangle, where this was the sun, the moon, and the earth. But it would have been interesting if these objects were arranged along the same straight line. If that is the case, then we would probably have the sun. Somewhere in the middle, we would have the moon. Somewhere there, we would have the earth. So my challenge to you would be, arrange these bodies as I have on this diagram and try to do the same calculation. Calculate the net force experienced by the moon. This distance was 2,1 times 10 to the power 11. This one was given as 4 times 10 to the power of 8. The main thing with solving these problems is always drawing a diagram. Always drawing a diagram, number one, and then showing forces on that diagram. So if I want the resultant on the moon, this tells me that the moon will experience a force in that direction due to the sun and another force in that direction. If I arrange them in the same straight line, the forces are going to be collinear. So I won't need to use theorem of Pythagoras. Okay. I think that's it from me for today on the gravitational force. But I want us to talk about something interesting, and I think I'm gonna need a clean sheet for this. So a clean one, you know. So I want us to just consider an object which is on the Earth's surface. I'm just gonna draw this object. This is the Earth. And then let us say the object is a person. And let us say the person has a mass of 80 kilogram. What I want us to do, number one, I want us to calculate the weight of the person. Or before we even calculate it, I want us to write down a formula to calculate the weight. To calculate the weight of this person, the weight is equals to m multiplied by g. This w is the weight. This is weight. Let me just write that. Small m is the mass. And then your small g, that is for gravitational acceleration. What is important here is that this is acceleration. It just have a specific name. Gravitational acceleration, meaning acceleration due to gravity. Okay, so we know that the gravitational acceleration on Earth is a constant. It's 9.8 meters per square second. When we talk about mass, this is the amount of matter in a substance. And the amount of matter in a substance, we are measuring it in units of kilograms. And mass is a scalar quantity worth mentioning. When we talk about gravitational acceleration, we know that acceleration is a vector quantity. So this is also a vector. When we talk about weight, hold on. What is weight? When we talk about weight, remember when we were doing types of forces, we said that the weight is a gravitational force. So this weight is a gravitational force. So I can write that statement as W is equals to Fg. But from that equation above, I know how to calculate weight. Weight is equals to mg. So here I can replace the weight with the mg. So that is the mg there, which I wrote in light blue. Mg is equals to Fg. But what is Fg? According to the universal gravitational law, we said to calculate Fg, we can use G m1 m2 over r squared. In our case, what is m1? That is the mass of object 1. Which one is object 1? I'm going to say this is object 1. The Earth will be object number 2. So this will be the mass of the man. And the mass of the man, I'm going to leave it as m because I used m in that first equation. And then m2 will be the mass of object 2. What will be object 2? That will be Earth. Remember what r is. R is the distance from the center of the man to the center of the Earth. But we know the mass of Earth. The mass of Earth is something like 4.98 times 10 to the power of 24 kilograms, which is very large. So in this case, we can treat the man as a point particle. So I can come here and make the replacement. I'm saying Fg is equals to that. So it means where I see Fg, I can replace Fg with G, mass of the person, mass of the Earth, divided by R squared. Oh, now I see like terms. So I can divide both sides by the mass of the person. So if I do that, this equation now becomes small g is equals to g, that one there is gone. I have mass of the Earth divided by r squared. So what this means is if we want to calculate the gravitational acceleration, this is the equation we can use. This is used to calculate gravitational acceleration. Does not matter gravitational acceleration where. It could be gravitational acceleration on Earth or gravitational acceleration in some other place. I want us to talk about these variables. This is gravitational acceleration. This still has the same meaning. This is gravitational constant, the mass of the planet Earth. So looking at the equation, this tells us that G is independent of the mass of the object. But what does G depend on? The gravitational acceleration, number one, depends on the mass of the planet as well as r. What is r? R will be the distance from center of the planet to the point of interest. I think I'm going to leave it like that. Where's the point of interest? The point of interest could be some point that we are talking about or where that object is located. If we look at the diagram, what is our R? It is from the center of the Earth all the way to the point of interest. The point of interest is where we have placed the object. So that is R in the sketch. But if we look at R carefully, R from the sketch looks like the distance from the center to the circumference of Earth, which is the radius of Earth. So it in this problem, for this particular problem, small r is equals to the radius of the planet Earth. It's not always the case. Always draw out this r and see it for yourself. So it means we can actually use this formula and the interpretation of r from the diagram to try and confirm the value of small g on Earth. It will be g is equals to 6,67 times 10 to the power minus 11 multiplied by the mass of the Earth, 5,98 times 10 to the power of 24 divided by the radius of Earth, which is 6,38 times 10 to the power of 6 all squared. Okay, so if we confirm that calculation, 6,67 to the power minus 11 times 5,98 to the power 24 divided by the radius of Earth. Okay, if I perform that calculation, I find that G is 9,79908805 meters per square second. And if we round this off to 2 decimal places, it will be approximately 9,8 meters per square second. And that's where it comes from. So if we can come back to the equation of G, we are saying that G is equals to Gm, this is the mass of the planet, divided by r, the distance from the center of the planet to the point of interest all squared. So from this equation, we can plot graph of G versus m. We can plot a graph of G versus 1 over r squared. I'm going to leave you to plot G versus r squared for yourself. So if we want to plot this graph, remember we said you find an equation which has these two things, Gm over r squared, and what you're going to be plotting along the y. What are we plotting along the y, by the way? Remember what comes before the verses, you plot it along the y. What comes after the verses, you plot it along the x. This helps us to draw the axes. So it means we're having G versus m. So what I'm plotting along the y, I replace it with y. What I plot along the x, I replace it with x divided by r squared. So everything else must be kept constant. So y is equals to ax. What is a? Let a represent g over r squared. So this will be a straight line graph passing through the origin. There it is. What is the gradient of this graph? The gradient, we can go back from the formula. The gradient is the coefficient of x. It's a. What does a represent? It represents g over r squared. So that is the gradient of the graph. Okay, if we come back to this one, because I've been explaining this procedure for a very long time, I'm just gonna draw this one out. If you want to learn how to draw these graphs using formulas, you can go back to the video on gravitational law part A, as well as Newton's second law part A. Okay, so we have g versus 1 over r squared. This will give us a straight line graph. What does the gradient of the graph represent? Please feel free to pause and try this out for yourself. The gradient of this graph represents g multiplied by the mass of the planet. Okay, so now I want to go back to the question I was having. Where is it? Okay, it's this one. There was a question on gravitational acceleration. Let me unhide that question. Gonna need a huge eraser. Okay, so there's the question. It says calculate acceleration due to gravity, which is gravitational acceleration, at a height of 6 kilometers above the Earth surface. So there's the Earth, and we want to calculate gravitational acceleration at this point. How far is this point? We're being told that the point is 6 kilometers. Remember, r is the distance, so in physics, SI units are meters. So this will be 6 times 10 to the power of 3 meters. So we are saying to calculate g is equals to gravitational constant, mass of the planet. Which planet are we talking about? We are talking about Earth, divided by r squared. What is r? We said that r was the distance from the center of the planet to the point of interest. So that is r there. Okay. So this is the r that we need to, that is the r that we need to sub in red. But what do we know so far? We know that little bit over there, that is 6 kilometers. It means we must find that little bit. So from the diagram, we can clearly recognize that that little bit is actually the radius of the Earth. So what this tells us is small r will be equals to 6 times 10 to the power of 3. Let me use symbols first before I sub in. Okay, so it tells us that this will be the radius of Earth plus 6 times 10 to the power of 3. That will be 6,3. 8 times 10 to the power of 6 plus 6 times 10 to the power of 3. This should help us to find r. So now we can sub in g is equals to our gravitational constant multiplied by the mass of the planet 5,98 times 10 to the power of 24 divided by 6,38 times 10 to the power of 6 plus 6 times 10 to the power of 3 all squared. Therefore, g will be equals to, let me grab my calculator. Maybe I should ask, before we even get the answer, do we expect the answer to be greater than 9,8 or less than 9,8? Interesting. If we look at the equation and I locate r is there and then g is there. So it means if this is small, this will be large. If r is large, g will be small, because we have increased r. Remember when we started with the previous example, the object, the point of interest was here, so r was the radius of earth. Now we are adding something else, so it means that r is now large. We expect gravitational acceleration to be less than 9.8. So let us see if that is indeed true. 5.98 to the power of 24 divided by 6.38 to the power of 6 plus squared. Okay, so if I calculate this, I find that g is equals to 9.78 meters per second. So remember that other one was 9.799, and this one is 780. It's actually 7809, so 781. So we can clearly see that that is a decrease. So in the next video, we're going to talk about more about the relationships as well as the weight of an object in another planet. That's it from me for today. Till we meet again. Bye.